Can you guys hear me? Hello?
Yes, we can hear you.
Yes, I was not successful in launching the contents. I start again. So, okay, good. Okay, let me just load one more thing. Okay. Good afternoon. You can hear me. Can you see the contents on the screen? Hello?
Yes, we can see the content.
Okay, great. Okay, so let's first go to the left one. The left one, the content is still the notes of chapter 2. Okay, before I start today's continue the lecture, I'd just like to ask you, do you have any questions? Okay, if no, so let me just start, continue where we left last class. So last class, we finished the additional diode circuit. Okay, one is a photodiode detector circuit, another one is a LED lighting circuit. So next, okay, so we'll come to examples of diode logic circuits. And there are two diode logic circuits that we will show as example. Anyway, let's go to the first, the top one. The top one, we use the two diodes for example, and then do two control voltages. Okay, two control voltages at the input end. So this is V1 and this is V2. Okay, and this V1, V2 operates between 0 volts and 5 volts for that example, for the digital application. So here on the left, I have the table. The first two items are V1, V2, and the value of the V1, V2 as a control. Okay, first situation, both V1 and V2 are 0. Okay, so both this voltage is low voltage at the ground, this voltage is grounded. So it's a ground. You can see this side of the diode is almost grounded towards the ground. If you neglect the voltage drop at the resistor, and if V1 and V2 are 0, so the diode voltage is 0. So diode voltage is 0, then the diodes are off. So D1, both diode 1, diode 2 are off. If diode 1, diode 2 are off, nothing from input passes to output. So output voltage will be 0. Okay, so if we flip the V1 voltage from 0 to 5 volts, and this side is 5 volts, this is 0 volts, obviously we have sufficient voltage to overcome the threshold voltage of diode 1 becomes on. And for diode 2, because V2 is 0, so diode 2 remains off. Nonetheless, once one diode is on, so once V1 is on, there's a constant voltage step down V gamma, which typically we take as a 0.7 volts. So what's the output voltage you have now? It's just an input voltage V1, step down 0.7 volts. You get here 4.3 volts as output. Okay. If we flip the value of the V1 and V2, so V1 is 0, V2 is 5 volts on the third row. Well, then the diode 1 is off. Diode 2 is sufficiently overcoming the threshold voltage. So diode 2 become on. So the output voltage again is input voltage V2, which is 5 volts, minus 0.7 volts at diode 2, and you get a 4.3 volts. Okay, if both input are 5 and both diodes are on, and then if their specification are the same, step down voltage is 0.7 volts, then you also get output voltage of 4.3 volts. And digitally, we can take the low voltage as a 0 and high voltage as 1. So that is an OR gate performance. The second example, we also use two diodes. However, flip the direction of the diode, and on the triangle side of the diode, we connect through a resistor to a 5 volts power supply voltage. And V1 and V2 are still the control voltages. And in this truth table, we list out the control voltage from 0.05 volts, 5 volts again. Okay, this time, if both control voltage V1 and V2 are 0, so this is 0 voltage, this end is high voltage 5 volts, obviously diode 1 is full bias sufficiently, it's turned on. Like the same thing happened for diode 2, both are on. Diode 1, diode 2 are on. Once diode 2 and diode 1, diode 2 are on, so what's the output voltage? Our voltage is here. If both are 0 volts, but then diodes on, there's a constant voltage drop across diode 1, 0.7 volts, same constant voltage drop at diode 2, 0.7 volts. So what you get output is 0 raised up 0.7 volts, so output voltage is 0.7. If one of the control voltage turn to 5 volts, say for example V1, this ends 5 volts, this ends 5 volts, the voltage drop on the diode will be 0. So diode 1 should be off, as indicated here. However, V2 still remains 0. So while D1 is off, D2 is full biased sufficiently and become on. Once become on, then there's a finite voltage step up, 0.7 volts from here to here. So have a 0 plus 0.7, output remains as a 0.7 volt. If you flip the value of V1 and V2, and the end result will be the same. Instead, we have diode 1 on and diode 2 off, but the output result will remain the same as 0.7 volts. What happens if both inputs are 5 volts? This is 5 volts, this 5 volts, diode 1 is off. This 5 volts, here's 5 volts, diode 2 is off. When both diodes are off, nothing from the left-hand side propagates to the output. So basically, you break this part. So what's output voltage? Output voltage is tied just to the plus 5 volts. So this circuitry performs as an AND gate. So this will be the example. Okay, we use diodes to implement the basic logical gates. Okay. Any questions? No question? Okay, so we'll go to the next one. Okay, so it's almost like a most complicated situation of chapter 2, multi-diode circuit. Okay, and actually here the sense of multi-diode circuit is different from previously the circuit we studied. Although we have multiple diodes, but those situations are straightforward. And for this section, the multi-diodes are sort of arbitrarily arranged. Okay, it's not as previously we studied like rectify. We purposely arrange in a direction to achieve a rectification, to achieve a voltage doubler, and so on and so forth, or the logical gate. And here we have a general multi-diode circuit. Means you have more than one diode. In this case, we have 2, and they may contain the circuitry such that their orientations can be arbitrarily placed and put in some sort of a bias voltage somewhere here or somewhere there. So it's a very generic multi-diode circuit. How do you analyze this generic multi-diode circuit? Well, you have to fall back to determine whether determine means confirm whether each diode is in the condition of on or off. If it's on, there's voltage drop step down. If it's off, then you break it, let it become open circuit. The question now is, because we have 2 diodes, how do we know which diode is on, which diode is off? So theoretically speaking, you have 2 diodes, then there are 4 possible combination of the state of 2 diodes, whether both diodes are on, or one diode is on, one diode is off, or the other way, or both diodes off. So you have 4 possible situations. Well, looks like you may have to analyze the circuitry under these 4 conditions or 4 situations, and you calculate, and then you figure out which one is the correct answer. But that's too tedious. Okay, if you have a 3 diodes, it means you have to analyze 8 situations. Okay, if you have a 4 diodes, you have to analyze 16 situations. Okay, you calculate this, 8 times 16 times, that's a lot of work of calculation. Here I show you sort of a more schematic or guided approach, the example. And in this multi-diode circuit, we do some simplification such that the forward resistance we take as a 0. Let's neglect the role played by the forward resistance when the diode is off. However, each diode may have we have to take into account the finite turn-on voltage. So in this example, both diodes, the turn-on voltage remain finite, 0.7 volts. And in this particular circuit, the input voltage we put in the 5 volts. Okay, let's see. Okay, so this information. Well, now let's see the configuration. This reference, okay, ground 0. And this is 5 volts. 5 volts is a fairly large voltage. And can you see the configuration? You trace your eyeball. 5 volts from here, go to this diode, a step down voltage to 1 volt, and go to this way. What do you see? Okay, arrangement wise, diode 1, diode 2 are under forward bias or under reverse bias. Okay, what do your eyes tell you? Any one of you want a response? Okay, anyone volunteer to comment whether diode 1 is in the configuration more likely forward bias or reverse bias? And what happened to diode 2? What can your eyes tell you?
Is it reverse bias?
Reverse bias?
Is it?
Oh, reverse bias. Okay, let's go to this way, the configuration. Okay, I'm trying to, okay, I hope you respond to my question. So if your answer is not right, then I will point you. Okay, it looks like you have some incorrect, okay, concept. So here, let me see if I can pull out the, chapter 1. Okay, so let's add one more no slide. Okay, open that, take some time. And just remind you, today's Thursday. In 2 weeks, we'll have a first midterm exam. Okay, so anything your knowledge is insufficient, in deficiency, you have to really pick that up quickly. Okay, so this chapter 1. Okay, so let's quickly go to review your knowledge. So what's the forward bias condition? Forward bias, the positive voltage should be applied at the P side, the negative voltage applied to N side. If a reverse bias is the other way. And this is the PN junction. The PN junction has a circuit symbol. That's a circuit symbol. This is P side, N side. And diode voltage nominally defined as a plus sign line up with P, minus sign polarity line up with N. Or the other way to say is a plus polarity line up with a triangle, minus polarity line up with the bar, this side. If a VD is really positive, then it's a forward bias. You are here. If a VD is the other way, that's reverse bias. Okay? Are we on the same page?
Maybe.
Maybe. Let's check. So, this side is low voltage. These are high voltage. Do you see D1, D2 are more or less in the forward orientation, or no, forward arrangement, forward bias, or reverse? Where's the high voltage side? The high voltage side this side or this side?
It's on the right side.
High voltage is on this side?
Wait, no. It's on the left side.
Right. This is 5 volts, right? It's very hefty. So these 5 volts, almost you can imagine this high voltage, this low voltage. So the high voltage side this side, low voltage side this side. So D2 should be 4 bias. Likewise, D1 is 4 bias. You may say you're putting a battery there, but this battery, if qualitatively speaking, you have 5 volts here, you have 1 volt there, this side looks like it's still higher on this side. So my eyes will tell me, okay, qualitatively, both sides looks like in the configuration of under 4 bias, not reverse bias. Okay? So if you previously thought it's okay, both sides under reverse bias, you have to really figure out why you conclude that way. That was incorrect. Okay. What that incorrect means, qualitatively speaking, where's the high voltage side, where's the low voltage side? So look to me. Yes, please.
Isn't D1 reverse bias in terms of the battery?
No. Not necessarily. Okay, suppose if we, as I said, okay, if we temporarily, neglect the voltage drop at the resistance, try to make the sort of judgment quicker. So if we neglect the voltage drop at here, then if the D2 is on, this is 0.7 volts. Okay, this is 0.7 volts. You add up at this point, just what? 1.7 volts, right? But this side is 5 volts. 5 volts is a lot more than 1.7 volts here. So this is D1 is still 4 bias.
Okay, thank you.
Okay, right. Just a sort of a rough eyeball tell you. You have 1 volt, but 1 volt compared to 5 volts, that's a small amount. So, but if this is a 4 volts, then that's different. If this is 6 volts, that's different. But right now, we just say 1 volt. Okay. What? I'm just telling you, okay, qualitatively, my initial guessing. So we start initial guessing, the best guess we can get. So we assume D1 on, D2 on, because they look like a 4 bias, sufficiently high voltage 5 volts. So once 4 bias, what's the output voltage? Input is a 5 volts. Once it turned on, then there's a 0.7 volts drop down, V gamma 1. Then there's another voltage, VB, drop down 1 volt. So output voltage should be equal to VI subtract V gamma 1 subtract VB, as given by this equation. So VO equal to VI minus V gamma 1 minus VB. So going here, step down voltage, subtract this voltage, you get output voltage. And putting the numbers, you have a 5 volts minus 0.7 minus 1, you get a 3.3 volt. That's why I claim here 5 volts. We kind of say here is a 3.3 volts, and this is sufficient for biasing the D2. Once we initially figure out this point is a 3.3 volt, then I try to figure out the amount of current ID1, ID2. To do that, first, I want to calculate the current through the resistance, R1. How do you figure out the amount of current through this resistance? I use Ohm's law. If I know the voltage drop between the two ends of the resistor, then divided by the resistance R1, I get this current, IR1. So what's the voltage drop across this resistance? And this resistance is in parallel with this serial combination of two components, which has a 0.7 volts plus 1 volt. Then that's this equation, IR1 equal to V gamma 1 plus VB divided by R1. And you substitute the value of 0.7 volts plus 1 volt, which is 1.7 volts, divided by resistance R1, which is 1.7 kilo ohm, you end up calculation 1 milliamps current going this way. And next, I want to find out what's the current in this branch. So this branch, the current is labeled as ID2. I also call it equals the current IR2, this IR2. So ID2 is the same current as IR2. How do you calculate this branch current? Well, we know this voltage is 3.3. If I subtract 0.7 volts, I get this voltage. This voltage subtracted 0, that's voltage drop at the resistor. Divided by the resistance R2, I get this current by Ohm's law. So it's a VO is this voltage minus V gamma 2 and divided resistance R2. And these are formula numbers. And if I carry out these numbers, I get a 0.65 milliamps in this direction, in this branch. All calculation looks like okay, until we check every piece. So what's the last piece we need to check? What's the current in this branch or current passing through a diode 1, ID1? Now you have a Kirchhoff current law you need to apply. Current IR1 plus current ID1 equals ID2. Okay? This current sum this current equals this current. Put the other way, if I know this current, I know this current, then I can figure out the ID1. So that's the formula. ID1 equals ID2 subtract IR1. And putting the number, I end up with minus 0.35 milliamps. You saw I put big red cross there. Means what? No, something wrong. Okay? Well, first, we all use piecewise linear model. Can you expect, or you can expect a diode current to be positive, that's fine. Can you ever will get the negative current out of the diode? In terms of your knowledge? No. Okay. On the piecewise linear model, diode will be either off, then the current is 0, or on. Once it's on, the current is positive. And now we find the current calculation value-wise minus negative current means that's impossible. That's impossible under forward bias condition using piecewise linear model. So that's a big red cross I'm showing here. No, something not right. Well, something not right. Where went wrong? Then you have to ask yourself, in each step, when I apply the physical law to derive the equation, is this equation correct? Is this equation correct? Is this equation correct? My claim is all those equations are right. But all those equations are right. Did I make any numerical errors? Well, I can guarantee you, okay, I didn't make numerical errors in this or this calculation. Well, you can say if nothing went bad or went wrong, then why the final outcome is wrong? Here, we trace back. Before all those equations, I made an assumption. I assume my visual eyes telling me looks like both diode 1, diode 2 are on. So basically, if I didn't make any step-by-step calculation, if final result is not reasonable, not sensible, that means the initial assumption must be incorrect. So which part is incorrect? Did I incorrectly assume the state of diode 1, or did I incorrectly assume the state of diode 2? Or this calculation says, well, diode 2 seems fine. Okay, these are 4 bias. If you're looking at this branch, this 5 volts, if I go here, diode 2 should subject to sufficient 4 biasing. So diode 2 should be on. Only thing is, looks like initially we assume diode 1 is on. It's our initial guess, even my initial guess, turned out to be incorrect. Okay, if diode 1 is on, then the diode 1 current should be positive. But here we say it's negative current. That means something wrong with the initial assumption of diode 1. So that says first part calculation, okay, settle, okay, we figure out diode 1's assumption was not quite right. So I redo the problem. This time, I will say, okay, if diode 1 is not on, then it's off. So let's treat diode 1 is off. But I said diode 2 still should be on because what? This is 5 volts. If you trace this path, and that's sufficient to turn on the diode 2. So we assume second time, diode 1 is off, diode 2 is on. So once we assume diode 1 is off, that means that you replace diode 1 by open circuit. So you neglect what happened in this branch. The current can only come from here, go this way, and go this way. Okay? So that just says diode 2 current, ID2, should be equal to the current passing through resistance R1 and R2. And in this case, I don't call that particularly the current in the R1, R2. I call the current going through the two resistors, so IR. So here the symbol IR, which I mean is both the current passing through the R1 and R2. Right? How do you calculate this current? I'm using Ohm's law. Ohm's law means I want to find out the voltage drop between the resistance R1 and R2, which I can find using the input voltage of 5 volts, VI. And then if diode 2 is on, there's a finite voltage step down, points V gamma 2 here. I use VI, subtract the V gamma 2, the rest voltage is dropped between among R1 and R2. So this voltage VI minus V gamma 2, and if I divide the total resistance R1 plus R2, and that's this amount of current. This is 5 volts minus 0.7 is 4.3 volts. Divide the total resistance is a 4 kilo ohm plus 1.7 is 5.7 kilo ohm. The number, end up with 0.754 milliamps. That's this current. Well, okay, once you calculate this current, I want to find out what's the output voltage. How do you find the output voltage, VO? Here I have two expressions, two formulas. I can calculate them in one of the two ways, actually either way. Output voltage equals input voltage, step down minus the voltage drop across resistor R1. So it's VI minus R1 times current IR. Right? So that's from 306. Another way to calculate the VO is what? I know there's a voltage rising here, V gamma 2. If I add the voltage rising at the resistor R2, that's VO. So the second expression is V gamma 2 plus R2 times IR. And here, there was a typo in the original the PDF file, which says R1. That's incorrect. So this is R2. So make a note there. So you're either using this equation to calculate the output voltage VO, or use this one to calculate output voltage VO. Both will give you the exact same result. It's a 3.72 volts here. At this point, it looks like if the question is asked you to find out what's the current voltage, output voltage VO, we find it. If asked what's the current in each diode, we say, oh, diode 2 is a finite current, diode 1 is off. When diode 1 is off, current is 0. Looks like you almost finished all the answer. However, if I ask you, tell me, if you claim diode 1 is reverse bias, so it's off, then I ask you, could you tell me exactly what's the voltage? Now we have a diode 1. Okay, How do I find the voltage drop at diode 1? Well, we know the output voltage VO here. So if a VO add up 1 volt, we get this voltage. And this voltage, okay, I label it here as V1 prime. I just label it V1 prime. So V1 prime equal to VO plus battery voltage VB. VO is 3.72 volts. Battery voltage is 1 volt. So we have a 4.72 volts. So 4.72 volts is what? You have a 3.72 volts rising here, rising further 1 volt. You have a 4.72 volts here. So what's the voltage drop according to diode? That which is VI 5 volts minus 4.7 volts. That's a diode voltage. So that's VI minus V1 prime. And then it's 5 minus 4.72. And you get 0.28 volts. So initially my guessing was still correct. So I'm claiming D1 is under 4 bias. But what it turned out to be what? D1 is 4 bias, but this 4 bias just be what? 0.28 volts. It's not, it's less than the turn voltage of diode 1. So it's not, it's a 4 bias, but just not sufficient 4 bias. So that's the reason diode 1 is off. Nonetheless, once we calculate these steps, we confirm diode 1 is off. So basically consistent with the second time the assumption. So once we confirm the assumption, all those calculations will be correct final answers. Any questions? Okay, no, so let's give you the second example.
Professor,
Yes, please.
can you explain what V1 prime is? Is that a derivative of V1?
No. No, it's just label. It's just label. Okay. I could just use it as a V1. So it's a label.
So is it
Voltage at this point above ground.
then what is V1?
As I said, it's just a label. Because if I label V1, sometimes, okay, eyeball-wise, people may confuse, call this as a V1. This actually is a VI. Just symbolize. I don't want to use a slightly different symbol. I could call that a VX. Okay.
Oh, that's a VI on the source? Sorry, I've been looking the entire time thinking that was the derivative of the source.
No, source is a VI. I is input. Input voltage is VI, is 5 volts. This VI. This voltage, we apply voltage 5 volts here between this point and the ground.
So V1 prime is the voltage between the diode and the battery in the source.
No. There's no voltage between diode and battery. This is a piece of wire. So there's no voltage drop between this point. V1 prime is, I'm saying, is voltage labeled at this point, but all the measurement is at this point to my ground. So this is V1 prime. Okay, between this point to this point.
So it's between the diode and the battery with reference to ground.
No. You use the words, a few pieces of that, your words is right, but put together, totally incorrect. It's between this point and that point. V1 is the point here, but it's measured all above the reference ground. So it's between this point to this point is my V1 prime.
So it's between D1 and VB? I don't know what this point and that point are.
V1 prime point is this point. But the V1 prime voltage, because you learned from 306, voltage is a property between 2 points. You cannot claim what's the voltage at this point. Just I cannot claim what's the voltage between this point, at this point. When I say voltage at this point, it means what? Always say that's the voltage between this point and the ground. When I claim voltage at this point, it means nothing. You cannot claim voltage at this point is 5 volts. It is what? 5 volts is what? Between this point and my ground. Okay. Do you understand now? Voltage is a property between 2 points. If you cannot get this straight, you make almost rest of the class or all the calculations incorrect. Voltage is a property between 2 points. Do you get that? Just as a node voltage, you have a reference point. Where you node voltage is a node between this node and the ground node. So that's this. So between this node and ground node, that's called I call the V1 prime. Between this node to this ground, I call the VI 5 volts. Okay? So voltage is not a property at 1 point. Voltage is property at between 2 points. So the second example is this circuitry contains more complication. Okay, I have 2 diodes, D1 and D2, and I have a 2 power supply voltage. One is 5 plus 5 volts. I call that these 5 volts. That's symbolized from the circuitry from the textbook. But in my notation, I always label these as usually to be say V plus. So V plus equal to plus 5. At this end, I have another power supply voltage. I call the V minus. So V minus equal to minus 5 volts. Of course, you can say, why we say the volts at this point as I have a voltage? Well, all that says in this circuitry, there's a ground, and that ground is not shown up in this circuit. So somewhere in this ground, there's ground between this point and that point is 5 volts. Between this point to that point is minus 5 volts. Between this point to ground to this point is 10 volts. So that's just it. That's a ground in the circuitry. You're supposed to learn that from the 306 knowledge. So once you have a complicated circuit, 2 power supply voltage, 3 power supply voltage, 5 volts, minus 5 volts, 10 volts. I even have a current source, 5 milliamps. Here it's called I, and in my notation, I call it I sub S, source. I have 2 diodes. I need to guess, the diodes 1 and 2 more or less subject to 4 bias or reverse bias. Then you look between this 5 volts, this minus 5 volts, between this point, the total difference voltage is 10 volts. 10 volts, plus side on this side, negative side on this side, diode 1 looks like 4 bias, diode 2 looks like 4 bias. So I assume diode 1, diode 2 are 4 bias. They are on. 4 bias and subject to 10 volts, that's sufficient to turn on the voltage, I thought, okay? So once diode 1, diode 2 are on, how do I figure out this the current ID1? So ID1 equal to V plus, that's this voltage, minus V gamma 1. I call this voltage VA, also reference to the ground. So this voltage subject to V gamma 1, subjective voltage is voltage drop at the resistor R1. Divide the resistor R1, I can find out the equation to determine ID1. How do I determine the diode 2 current? I have this voltage VA, and this side minus V gamma 2, VA minus V gamma 2. I get this point. If I subtract this side voltage is minus 2, V minus V minus, divide the resistance R2. In theory, I derive the equation to determine diode 2 current, ID2. Well, that's not all the story. You can say that's ID1. By the equation, I can calculate this. ID2 calculated by the second equation. When there's a third current coming in, IS. I call the IS in the book's figure called I, but I want to use IS, source current. So basically, source current IS plus ID1 sum up equal to ID2. So IS plus ID1 equals ID2. All these are based on Kirchhoff laws and Ohm's law. And substitute the value of IS equal to 5 milliamps. ID1 by this mathematical equation equals the right-hand side of this by this, I substitute the value. So that's a single equation. We can determine the quantity, unknown quantity of VA. And we find the VA equal to 6.033 volts. Of course, this voltage is not saying what's the voltage at this point. It means that's voltage between this point and my ground. Okay? Once I find the voltage VA, then I attempt to calculate what's determine the current ID1. So basically, once I find out this value VA, I calculate ID1. I repeat this equation here. Such a value of V plus 5 volts, V gamma 1.7 volts. Now VA, I'm able to substitute the value of 6.033 volt. Divided by resistance R, so it's 2 kilo ohms. It's here. So this R2, 2 kilo ohm. Well, unfortunately, I also get a negative current. So there's something wrong in determining the current ID1. ID2, I use this formula. All the calculations seems normal. So something wrong is ID1. So basically, as we said before, by piecewise linear model, the current diode current can either be positive or zero. Once you get a negative current, something wrong. So what's wrong? The assumption D1 is wrong. So let's go back away from that assumption and assume now D1 is off. And D1 is off, D2 is on. D1 is off, there's no branch involved in this part, then the current can flow from this to this to this. So that current ID2 really just coming from the source, 5 milliamps. So ID2 equal to IS equal to 5 milliamps. So, and how to determine the voltage VA? VA is what? From the ground up to the point, I get a minus 5 volts. If I can add up the voltage rise at the resistance R2 by Ohm's law, add another voltage rise, V gamma 2, I get a VA. So that's the equation. V minus plus voltage rise at resistance R2 plus voltage rise at the diode 2, V gamma 2. So VA, I have to use minus 5 volts. And Ohm's law calculation, the resistance times the current plus V gamma 2 is 0.7 volts. I get 8.2 volts here. So second time, I determine that voltage between this point and ground is 8.2 volts. Okay. So once 8.2 volts, you can verify why D1 is off. Because what? Here is 5 volts. Here's 8.2 volts. Of course, the diode voltage D1 is what? V plus minus VA. V plus V plus minus VA. So it's a 5 minus 8.2 volts. Actually, it's turned out to be minus 3.2 volts. So not only diode 1 is off, actually it turns out that one, the bias condition is reversed. It's a reverse bias. So now that no wonder diode 1 is off. Okay, so that's this. Then further, I have asked a question. What's the voltage drop at this current source? I don't know if you guys can tell me. Okay, are you able to determine the voltage drop at the current source? Okay. I know I taught this course before. I asked that question in the classroom, and some students would jump in to answer the voltage. There's no voltage drop at the current source. That's zero. That's incorrect concept. Okay. So if a source has no voltage drop, then you will end up to conclude there's no power supplied from the source. That's incorrect because the power is equal to voltage times the current. Current is 5 milliamps. If you say the voltage drop is zero, then there's no power supplied by the source. That's incorrect answer. So current source has a finite voltage drop. Only thing is I want you to determine, what's the amount of voltage drop across this 5 milliamp source. Then you know this source, the voltage at this end above ground is 10 volts. Okay, from this end is this VA above ground is 8.2 volts. 10 subtract 8.2, that's voltage difference between this point and that point. So 10 volts subtract 8.2 volts, you get 1.8 volts. So 1.8 volts actually is a voltage drop between this end and that end, or the voltage drop across the current source. Any question? If no question, then we finish chapter 2. Okay, so now we'll move to chapter 5 slide. Okay, so chapter 5 slide.
Wait,
Yes.
what happened to chapter 4?
Not even you can say what chapter 4, chapter 3. Okay, if you're looking for the contents, okay, chapter 3 and chapter 4 are the subject of a field effect transistor. Chapter 5, chapter 6 are bipolar junction transistors. So I determine, okay, after talk about the diode, I want to discuss bipolar junction transistor first. So we will finish chapter 5, chapter 6, and come back to chapter 3 and chapter 4. Okay, there's no logical relationship, but just I want to discuss it, okay, bipolar junction transistors first. Okay, if you're looking for the diagram, okay, you can see why, okay, I discuss this. Okay, the diagram say bipolar junction transistor. Okay, the slide.
Fascinating. So are we doing chapter 3 or chapter 5?
Chapter 5, and
Oh, I
then
thought
you
said
know,
chapter 3.
huh?
Sorry, I thought you said chapter 3.
Okay, let me just clarify that one more time. Chapter 3, chapter 4 are discussing about the field effect transistors. Chapter 5, chapter 6 are discussing bipolar junction transistors. Okay, I decided to discuss bipolar junction transistor first. Okay, so that's why we run into chapter 5, not chapter 3. So that's a slide I load to you. That's chapter 5. So this is a bipolar junction transistor. Actually, if you material structure-wise, you can see, okay, there are two types of bipolar junction transistors. One is called NPN, the other is PNP. NPN is on top, PNP on the lower one. So let's first discuss using the example of NPN to discuss that. There are three material regions, NPN. So that's why material structure-wise, okay, it's a simple. Okay, it's a kind of extension from what we just discussed, the PN junction. That's why I feel it's much natural. And once you learn the PN junction, then I put in one more region. Okay, then we can use our knowledge learned from the PN junction diode to understand the bipolar junction transistor. That's a rational. I go bipolar junction transistor, chapter 5 first. So here just says a statement says bipolar junction transistor has three separately doped regions and NPN. Between this interface is a PN junction. I call it the base emitter PN junction. Between this interface is another PN junction. I call it the base collector junction. Okay. By the way, the three terminals, three material regions. Okay, this is a name. Okay, at least at the book, the region on the left we refer that as an emitter terminal. The middle one is the base. Okay, the right side is collector terminal. So it's a three terminal device, three material regions. But between the three material regions, you have two interface. Two interfaces are two PN junctions. So we learned PN junction. So all those knowledge I will use here. Okay. So all depend. I really assume you understand well the PN junction. So now we use that knowledge to understand the bipolar junction transistors. In these three doped regions, however, there are differences. Not only the donor or accepted differently, but the concentration, doping concentration is different. The highest doping concentration is in the emitter, which is typically on the order of 10 to the 19 per cubic centimeter. Then in the base region, the doping concentration is lower by 2 orders of magnitude. 10 to the 17th per cubic centimeter. Collector, you have least amount of doping put in. It's lower, okay, by another 2 order magnitude, 10 to the 15th. So you doped, but they doped different amount. Okay. Plus, the space region, material-wise, structure-wise, we make it very thin, fraction of microns. Okay. Opposite is you have a PNP structure. Okay. So let's learn the principle of bipolar junction transistors. So this is a big concept. It's called a forward active mode. Okay, here we use an NPN transistor to illustrate this concept. So the material-wise is NPN. Okay, here when I say NPN means NPN bipolar junction transistor. NPN. Emitter is N, base is P, collector is N. The condition to achieve forward active mode is here. I highlighted in the blue, means important. Okay, PN junction between the base and emitter, I call the base and emitter PG junction is under forward bias. The second PN junction between the base and collector, I call the BC, base and collector junction, is under reverse bias. Those are two big conditions to configure transistor into forward active mode. So I use power supply of VBB, connect the plus side on the P side, connect next side on the N side. So this junction is a forward bias. I use a second power supply VCC, the plus terminal connect to N side, the negative terminal connected to P side. So this PN junction is under reverse bias. So I use external 2 power supply voltage to achieve these forward bias forward active mode conditions. So next, let's see the consequences when we bias 2 PN junctions in this configuration. Base emitter junction is a forward bias. Well, this is just a diode. So under forward bias, majority carriers gets across. Okay, so majority carriers from the emitter, in this case the electron, get injected into cross this PN junction into the base. Okay, because forward bias. Once you inject, you have a lot of electrons coming, once injected here. But this region, the electrons, the minority carriers, very little electron. So you have a lot of electron right across the injection, but a few electrons here. So there's a electron gradient, imbalance gradient here. So you have diffusion. The electron injected in will diffuse across the base. And we want the base to be thin, so be easily diffused. Okay, so inject the electron, diffuse across the base, get to this part. Once I get this part, I'm seeing the second PN junction. The second PN junction is under reverse bias. Once under reverse bias, I have a strong space charge field. Strong space charge field pointing into this way. Okay, this way. So electron coming in, seeing strong field, boom, electron be swept across this space charge region. So this injected electron are swept by the space charge field in the second PN junction. Okay, hold on, please. Okay, someone called. Okay, I turn off the phone. So electron injected from the emitter to the base, diffuse across base, and swept by the space charge field, get into the collector. And these are a lot of electrons because the highest doping concentration in the emitter, those majority carriers get injected from the emitter to the base, diffuse, swept into collector. Okay. So I discussed what happened for the majority carriers out of the emitter. So next, we'll discuss what happened to the majority carriers in the base. The majority carriers in the base are the holes here. Because these 4 bias, holes will be diffusing this way. So majority carriers, holes and base that inject into emitter because this is 4 bias. And next, we discuss what happened to majority carriers in this region. Majority carriers in this region is enriching their electrons. But these electrons, because this is a PN junction under reverse bias, this electron cannot move this way. So this electron actually will move this way. Move the same way as the injected electron. Injected electron coming in here, coming there. And these electrons within the original, the collector region will move along this direction. These amounts are negligible because we said you have a lot of majority carriers in this highest doped region. And this doping region is 2 order magnitudes lower, and this region is another 2 order magnitudes lower. So the electrons in this region compared to electrons in this region is almost 4 orders magnitude lower. It's amount of negligible, but nonetheless, they are there, but they move into this direction. So the electron moving in this way corresponding the emitter current moving this way. Electron moving this way corresponding to collector current move this way. Holes move this way. Holes move this way, so the current going this way. Okay? So, and this diagram just graphically illustrates what I previously said. Under 4 bias condition, not under 4, under 4 active mode condition, the electrons inject into the base, diffuse across the base, and then swept by this space charge field into the collector. So this majority of electron emitted from emitter, they end up at the collector. And the holes in the P region, middle P region, moving this way, they also contribute to the emitter current, but it's only 2 order magnitude lower because you have a 2 order magnitude higher, amount of electron compared to the amount of holes here. So these are very tiny, although it's their contribution, but a tiny amount, this amount compared to this amount. There's some part of the electron, inject in the base, recombine with holes into the we call the electron hole recombination. This process is unfortunately exists, but we don't want that to happen. So we want to make this process as sort of minimal as possible. So what we do is usually you make the base region very thin, so they don't have much chance to recombine. So electron inject in, then end up with the collector. Any question? So this the bipolar junction transistor, particularly for the material called the NPN arrangement. Similarly, we can understand another type of bipolar junction transistor material configuration is PNP. So this illustration, so this is left hand side is emitter, and middle is base, N, collector is P doped, P material collector. And as we said, for active mode, there are 2 conditions. One is what? Base emitter junction must be 4 bias. Base collector junction must be reverse bias. Okay? The 2 statements remain the same. So this base, this emitter, this PN junction must be 4 bias. How do I 4 bias this junction? So I flip external power supply VVV with plus terminal applied to P, negative terminal applied to N. So I make this PN junction 4 bias. But the base and collector junction again must be reverse bias. How do I achieve that? So I flip the external power supply voltage, the polarity VCC, flip plus side. Now the plus terminal is on this side, applied to PN, and minus terminal applied to N side. Sorry, did I think I just made a mistake. The statement. Okay, we want to make this PN junction base and collector be reverse bias. So the reverse bias voltage, then the plus side of polarity apply to the N, minus side of polarity apply to P. That's reverse bias configuration. So I make this reverse bias and this PN junction forward bias. Well, the consequence will be similar to previous description. You can see my paragraph here under this dot. Okay, still the same concept. Majority carriers from the emitter are injected into the base. It's the same thing because this forward bias, majority carriers will be injected into the base. Only thing is here is what in the PMP configuration, majority carriers in the emitter are holes. So in this case, majority holes are injected from the emitter to the hole, the base. They diffuse across the base, and then you have a strong space charge field, and they will push into the collector. Okay, so this paragraph is almost the same as previously. Only thing is now is that the action, tracing action for the holes. How about the majority carriers in the base? They are electrons. Electron on the forward bias in this PN junction, electron moving this way. Electron moving this way. So this is majority carriers, the electron in the base are injected into the emitter going this way. There's some electron hole recombination occurred here again, and we want that as small as possible. So we make the base very thin. And how about the majority carriers in the collector? This P region, they are holes, okay? But this reverse bias. On a reverse bias, majority carrier holes cannot move in this way, holes will move in this way. So they move the same direction as the injector holes. The amount is small. The amount, the orange unit, the majority carriers in the collector P region is 4 orders of magnitude lower than the amount of carriers out of the emitter. So they are negligible. Any questions? So if you don't call that a holes or electrons, but you just try to understand what happened to the majority carriers in the emitter, what happened to the majority carriers, from the emitter to get to the base, what happened to majority carriers from the base, or what happened to the majority carriers in the holes. These two 4 bullets statement are the same, except material configuration, they just turn opposite. One is NPN, the other is PNP, or actually say the electron and holes are just a swap, the roles. Okay. Because the electron and hole swap roles, for this example, the holes moving this way, then the emitter current is lined up the same direction of this current. So external emitter current pointing in this direction, external collector current pointing in this direction because hole carries a positive charge. Okay. Electron moving this way, they are associated the base current moving this direction. So the current from the external current, emitter current, base current, collector current, just flip opposite direction as NPN. So NPN, the current electron moving this way, but the associated current is moving in opposite direction because the electron carry negative charge. Electron moving this way, the current moving this way. Okay, for the holes moving this way, the direction of IP also going this way. Okay, so the direction of current flip, and external power supply voltage also flip. That's only difference between PNP and NPN bipolar junction transistors. Any questions? And here I summarize all of the discussion into words, into the equations. Okay. So, okay. So while I'm discussing this, the right hand side, I use the configuration. See by the left hand side. to just go back and forth referring to each other. So bipolar junction transistor current, there are three currents we need to discuss. The current at the emitter, the current at the collector, and current at the base. Okay, so what contributes to the emitter current, i.e., emitter current is coming from when PN junction between base and the emitter is 4 bias. So this PN junction is 4 bias, so it has a large current. So emitter current is diode current. Okay, so it's exactly the same expression of diode current. Okay, it's IS is the reverse saturation current. VPE is the diode voltage, and the VT is the thermal voltage -1. Because under 4 bias, then the terms in the paragraph, the second one, this one, -1 can be neglected. It's under 4 bias. So we neglect this one. So keep mostly is determined by this one. And that as a diode voltage, this current is sensitively controlled by the diode. Diode current is sensitively controlled by the diode voltage VPE. So sensitively controlled by this voltage drop using this PN junction. This emitter current is mostly coming from majority carriers, injected from the emitter electrons. You may have a small amount of contribution from the base, the hole moving this way, but that amount, because the concentration, doping concentration in the emitter is 2 order of magnitudes higher than the concentration in the base, so the carriers coming from the emitter dominance. How about the collector current? And as we said, collector current really mostly coming from the injected electrons. So collector current is from the majority carriers originally injected from the emitter. So they also, so it's proportional. So proportional, I call the IC equal to alpha F times IE, just proportional constant. This proportional constant is very close to 1. So it's about 98% or 0.98, 0.99. So the most of the carriers injected from the emitter end up at the collector. So here, so sensitively controlled again by this voltage VBE. How about the base current? Base current is a hose moving this way, and this 4 bias. So again, base current is coming from the hose controlled by the voltage VBE. And portion of that end up to the emitter, and portion of that be recombined. So the overall is still controlled by the voltage VBE, the same exponential control. So again, we can say they're all proportional VBE, e to the VBE divided by VP, all controlled by this factor, all controlled by this factor, so they're proportional to each other. So there's again another proportional way to relate the current. Say, collector current IC is proportional related to the base current. However, here beta is a big number. The reason is IB is very small. How small is IB is 2 order of magnitude smaller than IC. Okay, because the base dopant is less than the emitter dopant. So the IB is much less than IE. IE is almost equal to IC. Okay, so this is mathematically speaking. So all those current, to summarize, okay, this is a 3-terminal device. 3-terminal device, if I treat this as a black box, okay, black box, I only see 3 external terminals. So 3-terminal device, the Kirchhoff current law must be applied always. So this is generally true. Emitter current equal to the sum of base current and collector current. This is always true no matter what. However, in the forward active mode, there's further relationship. So collector current is proportional to the base current and can be expressed as proportional to the emitter current. So by two types of proportional relationship, either you use description as beta or alpha. Okay. If you use the beta expression, you substitute the IC into this Kirchhoff current law, you end up with IE equal to 1 plus beta times IB. Beta is a huge number. It's on the order of 100 to 100. So that's why IE is 2 orders of magnitude higher than IB. Because these two coefficients, proportional coefficient can be expressed in one way or the other, plus you have a generally true Kirchhoff current law, so you can derive the relationship between alpha and beta. Okay, alpha equals to the beta divided by 1 plus beta, or beta equals to the alpha divided by 1 minus alpha. As I said before, beta is on the order of 100 and 200, so this quantity is almost like a 0.99. So alpha is 0.99. So basically, most of the current coming from the emitter, they end up to the collector. And the other expression says because alpha is a 0.99, so 1 minus 0.99 is a 0.001, and this buffer equal to 1. So beta is on the order of 100 or so. Any questions? So finally, there's a circuit symbol, 3 terminal devices. So this NPN, and middle is base. Okay, this terminal is an emitter, this terminal is collector, and this is a transistor, bipolar junction transistor circuit symbol. Okay, 3 terminals, the flat side representing the base, and then 2, okay, this line, this collector, this is emitter. How this NPN, how you distinguish the emitter and the collector? Well, there's an arrow. The arrows indicate that's the emitter. Okay, the direction of the arrow really just point out the direction of the emitter current. So base current sum with the collector current must be equal to emitter current. It's for NPN configuration. For PNP configuration, they similarly define, except because the charge carriers flip from the electron to holes, so the current direction flip opposite way. Okay, for NPN, current IC flowing this way, IE flowing this way. For PNP, IE flows this way, IC flows this way, IB also gets out. Well, no matter what, IB plus IC still equal to IE. Okay, how to distinguish PNP and NPN? Only thing is by the arrow. So the arrow again is pointing inward and actually line up with the direction of the emitter current. So emitter current going this way, so the arrow is inward, moving this way. And this base terminal, this emitter terminal, the voltage drop between these 2 points is called the VBE. And this is the collector terminal, this emitter terminal, the voltage drop between these 2 points is called the VCE. Okay. Next class, we'll discuss more detail. The voltage current relationship for the bipolar junction transistor. Okay. This diagram, the table is copied from textbook, really sum up what I just said previous page. Okay, put in the table form. Really just sum up what we discussed here. Any questions? Okay. All right. So if no question, let me just tell you, remind you ahead. In 2 weeks, we'll have the first midterm exam. And I want you to be prepared logistically, be able to put your answer into the PDF form and submit it electronically. Okay, so you should be able to have a device, okay, be able to produce the results into the PDF form.
Will you be posting your old exams to study from?
No. Short answer is no. Okay, but I can tell you all the homework problems are relevant. So you can treat every homework problem as potential exam problem. So all the homework problems can be likely one of the exam problems. So whatever the past exam is the past homework, same.
So, which homeworks would we have to study for? Is it like homework from 1 till 4 or
No, okay, 1 to 3.
1 to 3?
Right. So whatever the homework I assign on Tuesday will be the last homework you can study for. Right.
Okay.
Okay. Yep.
Oh, for homework 2, I noticed in the solutions,
Mm-hmm.
there was a missing solution for question 1.50 part B. Will that be added soon or?
Um. uh, okay. Let's see if we're on the same page. I remember the homework problem 1.50.
Yes, 1.50.
It, if that's the case, that means I only asked you guys to do the homework problem 1.5A, not B.
Let me double check.
Right.
Make
Yeah, the
sure I'm
similar
not.
problem has A and B part. For the way to calculate that, I don't want to overburden you guys. I just say do the A part or do the B part. So I think that's the case.
Oh, I see. I see.
So the TA only
does
posts
say
the
just
solution
A
for the A
part.
part. Right.
Okay.
For the B
I
part, similarly, then you say that the equation steps are wise are the same, except the values are different, right? I assume.
Yeah, I did both A and B because I thought we had to.
Okay, you practice more. But did you find out that all the steps are about the same?
Yeah, they're very similar.
Right. So that's the reason I thought, okay, you do one will be sufficient. So for that part of circuitry, right?
Okay.
Other questions?
How long will we have for the exam?
Class time, 1 hour 15 minutes. But regular exam is 1 hour 15 minutes, still the 1 hour 15 minutes. But I will give you additional 10 minutes after the exam, so you have time to put the result convert it into PDF file and then submit it electronically. So
Okay.
yeah, so I can allude that once we do the review. But basically, the best maybe for you is you just regularly just put a piece of white paper, handwriting it, and then if you can scan into the PDF file, that's one way to do it. If you have a more advanced the electronic device, tablet, and if you're comfortable with writing that on the electronic board, you can save the result from electronic whiteboard into the PDF file.
So do we have to use the lockdown browser or do we just have to just join the WebEx during that time?
It's not a WebEx. I think I will post the problems on the Blackboard, and I will coordinate with the TA to see. They have more experience of what they did last semester, because last semester I was not at school, so I will just get some input from them. What's the best way? I think it's the
Last
Blackboard.
semester in 306, what we did, LaBerge had us do something similar where he just let us write it down into a PDF,
Right.
and he would just give us 24 hours to turn it in.
I understand that. Then, but for my class, 24 hours. I want just a regular hour 15 minutes, because I will not give you. It will be similar problem as I give you the previous semesters. The answer I expect to be answered within hour 15 minutes.
Okay.
Yeah.
So when exam time comes, do we just you just post the exam and then we submit it on Blackboard?
Right. So you see this exam problem on the screen. You just put a piece of white paper and then just start writing the answer, and then produce your answer, put it into the PDF file, and then just shoot to the Blackboard link and then submit. Just as you submit a homework problem, right?
All right.
Okay. So you're doing a homework problem, you're comfortable with the homework problem, then you should be comfortable with the exam problems.
Uh-huh.
Uh-huh. Okay. Well, I can give you some hint. Okay, the exam problems are very similar to homework problem. So if you ask what's the previous exam problem, yeah, actually some of the exam problems just homework problems, and some of the homework problems are actually you already doing.
All right, this seems doable.
Uh-huh. Okay.
Okay, I'm done.
Right. You just learn. Put it this way, you learn the concept, you learn the generic approach, the steps. Once you sort out, okay, I'm doing this problem, following this approach, follow this approach steps, then all the problems are just like a 306. You say, I'm doing the same approach as a node voting method. I'm doing the same approach as a mesh method. I'm doing the same approach as voltage division, current division, or the Thevenin. Okay, just using the approach, right? Yeah. But here we have a new approach. New approach is for the diode.
Explain the approach in our work, or will you just be able to figure that out?
It's not you figure it out. I lecture those approach. I gave the example in the lecture, and then you practice that homework to see did you master that approach. Okay. And then I will spend some time to maybe give additional time. Maybe I don't use the class time. If I don't use class time, I will find another time to give you a review that we can get more specific, like what approaches I hope you already learned. Okay.
Okay.
Right.
Wait, how many questions should we expect on the exam?
Pardon me?
How many questions should we expect?
No, 4 or 5.
Okay. Okay.
Right.
I have a question. Is there going to be partial credit awarded for the exam, or is it just going to be like, did you get it right or wrong? Or
Oh no, always partial. So that's why I will discuss or the comment that once we will get a review time. So some of the students maybe they have a habit from other class. They write a homework answer. They just write down the number. But here I expect you to practice your homework problem, write every step. That's a practice. And the exam, I also looking for the way you write every step towards the final answer. So that means my exam points are all distributed into the steps. Okay, so it's not the final answer, right or not right. You get a black and white the answer, so the point. So if you get a fifth steps right, you get a 3/5 points. So that's my philosophy. Consistent with that philosophy means you need to provide the answer in every step. So I can judge in which step you earned your partial credit. Okay? Did I answer your question?
yeah, thanks.
Right. Any further questions?
No, I think we're good.
Okay. Any questions? Bring out next class. Okay? Or at the time we do the review.
All right.
Okay.
Have a good day.
Have a good day too. Okay.